Okay, so I'm going to very quickly introduce neural networks and deep learning. I would like to wrap this and backpropagation within an hour. So I will have to rush through this material. Besides, my presentation will be very basic and very short. For those of you who want to learn more about deep learning, there is vast amount of material, both commercial, online. There are many books, many research papers, many websites and tutorials. They're not all of the same quality. So because I was asked a few questions during the break, I would like to make maybe a few recommendations. There's a book by Goodfellow that's considered a strong reference on deep learning. This is a reference book, so it's perfect if you already know about deep learning and you want a reference about it. It's not necessarily, to me, the best teaching material if you want to learn about deep learning. The best resource I could find is Andrew Ng's videos on Coursera. There's a machine learning course and there's a deep learning specialization. Andrew Ng is a professor of AI at Stanford. So his courses on Coursera are basically a trimmed-down version of what he does at Stanford. It gives you an excellent overview about deep learning. And if you want to dig deeper, like I did, for instance, a year or so ago, Stanford also posts their lectures and lecture material online, where you can dig the deeper technical aspects of it. So this is my recommendation. I'm going to introduce this stuff very briefly, starting with linear regression that we all know and love, and I will see how, in order to circumvent the limitations of such a simple model, we will naturally evolve towards deep learning. So a linear model, which corresponds to joint Gaussian assumptions on the input and the output, is that y hat, the best prediction that I can make for y, knowing the input x, that's a conditional expectation of y over x, that will be a linear combination of the xi's, right? So in this model, the x's, x1 to xn are my inputs as usual. My prediction is y hat. It's a linear combination of the x's. And the parameters are the weights of a linear combination as well as a constant, the intercept, that in machine learning lingo we call the bias. Okay? In regression problems, so-called regression problems, are those where we predict real numbers. And these are the ones that are of interest to us in finance. Typically, we want to predict, we want to estimate the price of a product, a risk management parameter, the cost of capital for doing some kind of business. What we really want is predict something that's a real number. In the machine learning community, if you read machine learning material and research papers, you will find that they're mainly interested in classification problems. So we have a photograph, which is a collection of pixels, which is a large vector of pixel intensities, for instance, and we want to know the probability that there's a cat in this picture, or a dog, or a human being, or whatever. These are called classification problems, where we're not trying to predict real numbers, but to predict probabilities that our inputs belong to a certain class. Now, since in finance we are mainly interested in regression, and regression is a bit simpler, I'm going to stick with regression in this presentation. But the good news is that everything I'm going to say almost identically applies to classification, and that in particular the mathematics are identical. So how do we fit a linear model? As usual, we have a training set of m examples that I'm using Andrew Ng's notations here. I will denote the example number 1 as x superscript 1 in parentheses. So each one of these examples is a vector in dimension n, and I've got m of these. And for all of these, I know the corresponding labels. I know the true values of y corresponding to this axis, which I denote also with superscript between parentheses y1 to ym. So what does it mean to learn the parameters of a model, where the parameters are the bias, which is a real number, and these weights, which is a vector in dimension n? Well, as usual, we're going to do that by minimization of prediction error. So we are going to minimize a cost function, which is the sum of squared prediction errors. And note that this is not just a back-of-the-envelope calculation so that we have a nicely looking straight line that goes through our cloud of points. This is actually backed with serious statistics, because this can show quite easily that this, to minimize this cost function, which is the sum of squared prediction error, is exactly the same as to maximize the log likelihood under Gaussian assumptions. Therefore, the parameters that you get by minimization of this cost exactly correspond to the maximum likelihood estimators of the parameters in the Gaussian model, and they have all the desirable properties of MLEs. So you probably know, if you don't, I encourage you to do this exercise, that the optimal B star and W star, so the parameters that effectively realize the minimum of the cost function, are found analytically, solving for the gradient of the cost to B and W being equal to 0. And the result that you find is the well-known normal equation that is written in matrix form, like this, where I basically gather the bias and the weights in one single vector, and the normal equation tells you that it's x transpose x minus 1 x transpose y. In other terms, an estimate of the covariance matrix of the inputs inversed multiplied by the covariance vector of y, in estimation of the covariance vector of y with the axis. Okay. Now, it's very good, but it's obviously limited, because linear models can only give us linear relationships between the inputs and the outputs. This is an important example, so I'm going to spend a bit of time on this slide, because I'm going to come back to this example repeatedly today and tomorrow. This is an example where we try to predict the future price in 1 year of a European option of some strike, and maturity 2 years. So what I'm trying to do here is I'm trying the machine to get the machine to learn how it can find the future price in 1 year of a call option of residual maturity 1 year at that time, knowing the spot price in 1 year, right? And I'm going to use as a training set some simulated data under Black and Scholes' assumptions, so that you and I know what is the correct value. It is given by Black and Scholes' formula, of course. The machine doesn't know that. We know that, so we can measure the performance of a machine in this very simple example where we know the correct value. So how am I going to do that? I'm going to simulate with basic Monte Carlo methods. I'm going to simulate the spot price in 1 year under Black and Scholes' assumptions. And in the same scenario, I'm also going to simulate the spot price in 2 years. And I'm going to take the maximum of this guy and minus the strike and 0. That will give me the payoff of a call option in 2 years. So this is all represented on this chart here, where each point in the cloud is one scenario with the spot in 1 year, the simulated spot in 1 year on the horizontal axis, and the call payoff in 2 years on the vertical axis. Okay? So what's important here is that we are not looking at prices of options or whatever. We are looking at payoffs. We are looking at realizations. So my X, my input, is the spot price in 1 year, which is a random variable. And my output, what I'm trying to explain from this input, is the payoff of a call in 2 years, right? And each point in this cloud is one scenario. Is this, I really need you to get that, so tell me if it's not the case, and I will explain it more. Yes? Okay. Okay. So, what we're trying to find is, if I know the spot in 1 year, for instance, is 150, what is the value of, what is the corresponding value of my call option? So I'm not trying to predict the payoff of a call option in 2 years by the spot in 1 year. That would be ridiculous. But I'm trying to predict the conditional expectation of the call payoff in 2 years, conditional to the spot in 1 year. In other words, the future price of this call in 1 year when I know what the spot is. And we all know that the correct answer is given by Black and Scholes' formula with maturity, the residual maturity, 1 year. And this is what's drawn here in purple. What is drawn in red is the result of a linear regression. And you can see that it's not so hot. It's not of such a good quality. It gives us a good approximation of the truth, a reasonable approximation of the truth around the money, but the extrapolation is completely off, and because it's a linear prediction, it also gives me some undesirable negative values for the call price, which we know is impossible. But I have to point out that the machine doesn't know anything about Black-Scholes. The machine doesn't know anything about how this cloud of point was simulated. The machine only sees this cloud of point and makes a linear regression. And this is the result. So how do we conventionally, traditionally circumvent these limitations? We have been for decades regressing on basis functions of x instead of regressing on x. And this is where we're starting to see this notion of a hidden layer and this architecture that starts resembling to a neural network. Because what I'm going to do is this is still a linear regression, this is still a linear model. The estimation y is still a linear combination, but instead of being a linear combination of the inputs, it's now a linear combination of some basis functions of the inputs. So I have a pre-processing step, a manual pre-processing step, that's not at all part of the model, whereby I take my input and I transform it by hand into a number of basis functions of the inputs. The simplest example is the polynomial regression. In this case, the basis functions will be all the monomials of the inputs up to a certain degree p. So for instance, I have all the monomials of the first degree, which are just the xi's, the monomials of the second degrees, which are the xi squared and the xi(xj), etc., etc., right? So in this example, for instance, I have 3 inputs. I have an input in dimension 3, and I'm doing quadratic regression, so polynomial regression of degree 2. So then my basis functions of x will be x1, x2, x3, x1, x2, x1, x3, x2, x3, and x1 squared, x2 squared, x3 squared. And we see something that typically happens in this case is that the dimension of my basis function of my, now this is what we are going to call a hidden layer. So the actual values that I'm going to combine in a linear combination to form a prediction, which are not my x's, but which are transformations of my x's in typically a higher dimension, okay? And what's important to understand here is 2 things. First of all, that the second step to get the prediction out of these basis functions is exactly a linear regression. It is the same thing as before, and it's also resolved analytically with the normal equations, only you don't take the x's, you take the a's into account for that. So this is still a linear model, this is still a linear regression, but on some transformations of my initial inputs. And the second thing that you need to understand is this transformation is arbitrary, and manual and independent of the data. It's not the model. The model just gives me the regression. The model doesn't tell me anything about how, looking at the data, how I should transform my input x's on into basis functions A. This is an arbitrary decision. I have decided, me, the user, once and for all, that I'm going to do a quadratic regression, and that therefore I'm going to transform my initial vector x into the vector of all monomials of x of degrees 1 and 2, right? So the model starts here. This is manual preprocessing, okay? So does it work? Well, yeah, kind of. It works. It works actually pretty remarkably. Here I have done a quadratic regression in the same example as before, and you can see that it's remarkable. Well, it's not perfect. It couldn't be used in production, for instance, right? Far from that. But it's remarkable how well it approximates the true result of Black-Scholes, knowing that all the model sees is this cloud of points. Now, I don't know about you, but me, I can't read anything on this cloud of points. To me, they look random. I certainly couldn't read Black and Scholes in there, but the machine does. And with an example so simple that it's been done without programming. This is just on Excel. There's a spreadsheet that I posted in the workshop. Here I'm giving you the link. You can look at it. This is a completely trivial exercise, and yet the results are not so bad. Mathematically, we understand why, because combinations of polynomials can approximate any smooth function to arbitrary precision. We know that. Hence, it can detect any smooth nonlinear pattern in the data, but only with a large number of basis functions, a high polynomial degree. That's why we're far from perfect here. Okay? So there are some problems with basis function regression. One of them, it's not shown on this graph here, but the extrapolation will definitely not be as hot as interpolation. This is a quadratic function, right? So, if I draw it a bit more to the left, it will start rising, which is not what we want. And you can see here that extrapolation is not going to work on the right side either. So extrapolation is a persistent problem when we're trying to do these things. And another problem is the course of dimensionality, which you kind of already see on this graph, because we started in dimension 3, and with a quadratic regression, we ended up regressing in dimension, 9? And this actually, it can be calculated with basic combinatorial. How many monomials do I have in a p-degree polynomial regression when the number of features, what we call features in deep learning, so that's the dimension of x, is n0? Well, we can see that n1 is an exponential function of n0. When you start seeing these exclamation marks, the factorials, we all know that it's going to grow quickly, right? But it's not good news. So for a quadratic regression, this formula simplifies to this one. So dimension grows, for instance, if I start at dimension 10, then if I want to do a quadratic regression in dimension 10, I'm doing a linear regression in dimension 65. If I start in dimension 100, I end up in dimension 5,000. If I start in dimension 1,000, I end up in dimension 500,000. So you can see how it can grow very, very quickly, because in practical applications, we're not looking at Black-Scholes, we're not looking at one simple European call. A dimension of a state vector is typically of dimension 10 to 50, not in dimension 1. And you can see how we are going to suffer from the curse of dimensionality with polynomial regressions or any kind of basis function regressions. And then, why is it a problem to be in high dimension? Why is it a problem to regress on a large number of basis functions of x? That's because of overfitting and the rule of 10. say if you fit a linear model with n free parameters and you have n training examples, right? Then in general, well, let's assume that you don't have any collinearity problems. In this case, you can find and you will find a perfect fit, right? But the model may not generalize well to new examples because it captured the noise of this particular training set. This is what's called overfitting in machine learning. I posted a little explanation on Quora about this error analysis, also called variance bias trade-off, and the notion of overfitting. So there are many solutions that I will not cover to overfitting. It's generally collectively called regularization, and this is covered in Stanford's machine learning class on Coursera, or if you prefer reading, another book that I would recommend is Bishop's Pattern Recognition and Machine Learning Classic. But of course, the most effective means to avoid overfitting is simply to increase the size of a learning set, of a training set. That's how you avoid overfitting in the most simple way. There's an empirical rule, and I insist, it's not a mathematical theorem, it's an empirical rule, a rule of thumb called Rule of 10, whereby we generally, it's recommended to have a data set of at least 10 times the number of parameters. So if you want to fit 1,000 parameters, you should have at least 10,000 training examples. And these training examples, they may be expensive to simulate or to find if you're not in a simulation context. And therefore, the dimensionality is definitely a problem. And this is one of the reasons why artificial neural networks actually perform a better job than basis function regression, because on my left here, I have basis function regression, as we have just seen, and on my right, I have an artificial neural network, and they look exactly the same, except that this initial manual preprocessing step is now part of a model itself. So with basis function regression, I'm going to arbitrarily transform my initial vector x in a vector y on which I will perform a regression. In a neural network with one hidden layer, what we call a shallow neural network, it is the same thing, but it's the model that's going to find the best possible transformation of the inputs from the data itself. So it's not me who is going to say, I want to regress on polynomial, on polynomial functions of x, and I may need a large number of these if x is big. I'm going to perform a regression, so the second step will remain exactly identical. The prediction will still be a linear combination of the hidden layer, just like before. But the production of the hidden layer will be made by the model, not by me. I'm just going to say, I want to make a regression on 50 basis functions of the inputs. I'm not going to tell which 50 basis functions. I will let the model figure out the best 50 basis functions to perform this regression from the data. This is what neural networks are about, automatic feature extraction. You don't decide what features you regress on. The model finds the best ones from the data. And we can see why neural networks have to perform at least as well as basis function regression, because in theory, they should be able to find functions which are at least as good as any arbitrary set of basis functions, since it's going to try to find the best one. So how do we do that in practice? How do we learn basis functions from the data? Well, we are going to use, let me use my gadget. We are going to use a parametric family of basis functions. We are going to say that all these AIs, all these units in the hidden layer, all these numbers that I will end up combining to find a prediction that where a certain function phi of x parameterized by some parameters theta I. So each basis function will be the same parametric function of the same vector of inputs x, but each one with different parameters theta I, right? And I'm going to find the theta i's that minimize, as usual, the prediction errors. So I'm going to find the best basis functions on which I want to regress, and I'm going to find them from the data. So I'm going to learn these parameters theta along with the weights W and bias B of the final regression by minimization of the cost of the sum of prediction errors, for instance, the sum of squared errors. Now, this defines a general neural network. The most common choice of parametric function is a special kind of neural network called the perceptron, which has some very nice computational and mathematical properties. And that's why in most of the literature, when you read about neural network, you don't see it in this form, you see it in this particular form, where this parametric function phi, they consist in a linear combination of the x's followed by an element-wise activation and an element-wise application of a nonlinear function. So we say, in the case of a perceptron, that each basis function, so again, each one of these a's here, is a nonlinear scalar function g of a linear combination of all the x's. So we are going, for each ai, for each ai, we are going to combine all the x's, but in a different way, with different weights for each one of the a's. And then we are going to apply to the result a scalar nonlinear function. Why do we do that? Because otherwise, the output would be a linear combination of linear combinations of x's. So we would be back to a linear regression. And we would have earned nothing from the start. So these a's, in order to be meaningful, they have to be nonlinear functions of the x's. And so what we say in the perceptron is that each a is a linear combination of the x's, a different linear combinations with different x's for each a, followed by the application of a scalar nonlinear function called activation. So this is actually illustrated here. So for instance, A3 will be a combination of all these x's with weights W3 and bias B3. So in matrix notations, I say that Z3 is W3 transpose X plus B3. And then the actual A is this activation function G, this nonlinear function applied to Z3, right? That's how I get my A's. And then my on the output layer, I have my prediction, which is, as usual, a combination of these basis functions. And I'm going to learn from the data, I'm going to learn, so G is given. That's the arbitrary choice here. What I'm going to learn is the weights of all these linear combinations. So each one of them is a vector of weights, so I'm going to learn a matrix of weights. I'm going to learn a vector of B's, and I'm going to learn the weights and the bias of a final linear combination. That's how it's going to work. But conceptually, it's important to realize that we're still in a basis function regression context. Only the basis functions are not going to be arbitrarily chosen. They will be determined, they will be learned by the network from the data. That's the difference, but it is fundamental. So the prediction now is going to be made in two steps. On step one, we are going to define calculate the hidden layer. And this is what's called a future extraction. So we are going to go from the input x in some dimension n0 to the basis functions a in dimension n1. And in the case of a perceptron, This is the formula. A will be a function, scalar function, nonlinear function G, applied to a linear combination of the x's. And the parameters will be a matrix of all the weights in dimension n1 times n0, and B, the biases for every single basis function will be a vector in dimension n1. Now this activation function G, this has to be a scalar function that's applied element-wise to the vector Z, which is given by this formula here. And only in step 2, once we have calculated these basis functions, this hidden layer, then we are going to actually make a regression over the basis functions to make a prediction as a linear combination of the basis functions. Yes?
So I'm curious about the nonlinear function, which is like D.
That's the next slide.
Okay, so we can preempt that. So I'm just really curious whether the network, the algorithm, the library, however we choose to call it, has a finite set of these nonlinear functions that it just sees which ones work best, or whether it's quote-unquote inventing them.
It's what's called a hyperparameter. So it's not chosen by the model, it's chosen by you, the users. That's a choice you make. You arbitrarily choose the activation function G that you're going to apply. What the neural network will learn is the weights of the linear combination. All in all, A will be G applied to a linear combinations of the axes. And that's your parametric function of the axes. The neural network is going to learn the weights, but you have to supply the activation function. And it's the combination of these linear combinations with these weights that are going to be learned and this activation function that you supply that give you the hidden layer as a function of the input layer.
But I thought that it was actually the network that was figuring out what nonlinear function makes best sense, because then it sort of adds rather limited value.
No, it's not true. It's not true on both accounts. It's not of limited value, and it's not the network which chooses the VJ. The principle is that you want A to be a parametric function phi of the x's with some parameters theta, right? So the network will learn the parameters theta, but you give the shape of a function phi. You say what parametric family you're going to use. And the network is going to learn the parameters. In a perception, we say that A is J of W x plus B. The network is going to learn the W and B, so that's a particular shape for a function phi, but you provide the activation. The function, the point is that it's the hidden layer that's a function of the input layer. And the network will learn the best function, but within the family of functions that you decide. And you decide that this family of function will be defined as a linear combination with learnable weights, followed by an activation that you decide once and for all. So all in all, the neural network will learn a function to go through, to learn the parameters of a function to go from x to A, but not the generic parametric family, the parametric shape of a function. So that's something for you to decide. A little bit like in statistics, you have a statistical model. So you decide that you want to use a Gaussian model, and you are going to estimate via MLE, maximum likelihood estimators. You're going to estimate what is the mean, the vector of means, and the covariance matrix of this distribution. But the model is not going to tell you, at least not this kind of models, if it's a Gaussian or not. That's something that you decide. It's the same here. You decide on a parametric family of functions that get you from X to A. The neural network is going to learn the best parameters, hence the best functions, but not inside this shape of this parametric family. On a perception, you say that the parametric family is a certain scalar function that's applied element-wise to a learnable combination of the x's. So all in all, this is a parametric family of functions which parameters have the weights and the biases. And this is what the neural network will learn. So it's not just, it can't just choose any function among any possible functions that calculate A as a function of X. It chooses within a family of parametric functions that you, the user, decide. But it finds the best parameters for these functions, hence the best functions within this family. Yeah? Okay, so in a second step, you make a linear combination of the A's with a different set of weights, W2, and a different set of biases, B, and that will give you the prediction. So that we saw. So now what is very convenient is to use a unified notation for both steps, if you want, because we can see that there are some clear similarities between the two steps. So if we use the notations that A0, and that's between brackets, so that denotes the layer number 0, my input layer, that's just X, that's my inputs. A of 1, the hidden layer, is what we previously called the A's, that are my basis functions. What we call prediction y hat, we call it A of 2, that's the output layer. And the activation function G, we are using different ones on the hidden layer and the output layer, because the output layer, we don't activate it, not in regression problems. So we say that G of 2 is just the identity, and G of 1 is what we previously called G. And then we get a unified notation for both layers. We just say that we get layer L from layer L minus 1 by applying a linear combinations with weights WL, with a weight matrix WL and a bias vector BL, followed by a by an element-wise activation G of L. And we find this guy, this equation here, that is the equation that defines a layer L out of a layer L minus 1 with a hyperparameter, the user chosen activation function for layer L applied to a linear combination with a learnable weight matrix WL and bias vector BL. So we have the same feed-forward equation now, or the same notations at least, for both layers. Now about these activation functions. Now we're coming from a financial background, so we would naturally be tempted to choose like Gaussian functions for activation. If, for instance, it would be natural to use the Gaussian cumulative distribution to activate smoothly above a certain threshold. Now remember that the only requirement for this activation function G is that it must be nonlinear. These are just some of the common choices, some choices that seem to make sense. If I want to activate very locally, if I want just to activate a very local region of a space, then naturally I would rather choose the Gaussian density, which is actually the derivative of a Gaussian distribution, as my activation function. And if I want, and in finance, I definitely want my extrapolations to be linear rather than flat, then my natural inclination would be to use an integral of the integrals of cumulative Gaussian distributions, in other terms, Bachelier functions, in a normal version of Black-Scholes, as my activation functions. Now, remarkably, in the machine learning community came out with very, very similar ways of activating, but which are much cheaper. They would typically activate with something like the sigmoid function, which has this shape, that's just 1 over 1 plus e to the minus z. And you can see that it looks pretty similar to the Gaussian distribution, but it's a lot cheaper to calculate. Right. So similarly, for a very local, if they want a very local activation, they would use the derivative of a sigmoid instead of a Gaussian density, and you can see again that it has a pretty similar shape. And in order to get linear extrapolation, instead of activating with the integral of a Gaussian distribution, we'll activate with the integral of a sigmoid, which has the benefit that it has an analytic expression, which is just log of 1 plus Ez, and that has this shape, which again is kind of similar to this one. So all in all, the conventional activation functions that have been applied in deep learning are pretty much cheap equivalent of Gaussian distribution or density or Bachelier, depending on what you're trying to achieve. More recently, people have found out that not all of these activation functions are equivalent in terms of learning, that some shapes of activation functions, I'm not saying that they're more meaningful, that depends on your problem and what you're trying to achieve, so it's not a question of meaning, but some shapes make learning, make the optimization easier and smoother. And so it has become a best practice to use these shapes. Now, people have found, for instance, that learning is made easier if the activation function is symmetric around 0. Another thing is that another thing you want to help the optimization algorithm is to avoid saturating the function too fast. You don't want the gradient. You don't want to you don't want your activation function to flatten too quickly, right? Because that would produce 0 gradients, and that would damage the learning algorithm. So for this reason, people now, instead of a sigmoid, use the hyperbolic tangent that looks just the same but translated on the horizontal axis, right? And instead of using something like this soft plus, this integral of sigmoid, people tend to use either ReLU, which we would call payoffs, or ELU, which has this form. Yeah, so it's g of z is z if z is positive, else it's it's, can't read here, but it's exponential of z minus 1. So that it's roughly symmetric around 0 and it doesn't flatten too quickly. So the reason why people tend to use the activations in the third column rather than the ones in the second column is simply to help the optimization algorithm. And the single column are cheap equivalents of the first column. That's how this works. So this is about activations. Now I'd like to see with you the fundamental notion of a computation graph, because in literature, usually people present neural networks, introduce neural networks by showing these graphs, and they tell you, okay, this is what a neural network looks like. Well, of course, a neural network doesn't look like anything. This is what we call a computation graph. So it shows you, it gives you a visual glimpse of the calculation involved to find a prediction from a set of inputs, and the order and the dependencies of this calculation. So that tells you that going from left to right, first you find the hidden layer, and each one of these hidden units will depend on all 3 or n inputs. And then you find a prediction by a linear combination of every one of these hidden units. And to go from here to here and from here to here, you apply the same feed-forward equation in a perceptron that looks looks exactly like this with a unified notations. So what is the computation complexity to the leading order? We ignoring activations and additions. What really takes time is the matrix product, WA, the matrix by vector product, because this is of quadratic complexity. And we have two of these. We have one to go from the input to the hidden layer and one to go from the hidden layer to the output layer. So the complexity to the leading order will be equal to n1, n0 plus n2, n1. So it's quadratic in the number of units and linear in the number of layers, 2 in this case. Okay? So how to train your perception? Well, you have a training set of m examples as usual. Remember, each one of your xi's here is a vector in dimension n0, and you have corresponding labels, the true values, the corresponding true values of y1 to ym. And we are going, the parameters that we are going to learn, coming back to these feed-forward equations, are all the matrices of weights and the vectors of biases for each one of these two layers. Okay? So we have two matrices of parameters and two vectors of parameters to learn. So we have, you can see, a large number of parameters, n1 plus n2. These are the biases, and these are the weight matrices. And we are going to do that, as usual, by minimizing the cost function, which is the sum of squared prediction errors on our training set. And note that in this case, we are learning the basis functions and the regression weights at the same time, because the basis functions will be given by the first layer of weights and biases, and the regression weights by the second layer. And there's no more analytic solution. Actually, see, this function, this cost function, is not even convex in the parameters. And we must apply a numerical minimization algorithm. Many iterative algorithms exist in literature. The simplest one, the one that's always described in textbooks, is gradient descent. You repeatedly move your parameters a small step down the steepest slope of a cost function, and we know that the steepest slope of a cost function is its gradient to the cost, is the gradient of a cost to parameters. So this gradient descent and other more sophisticated algorithms, they all require differentials of a cost function to all the parameters at every iteration. And the cost itself forces you to make predictions for all the examples in your training set. So in each iteration, we must compute not only the cost function itself by predicting m examples, where m can be a large number, but also its all the derivatives, all its derivatives to all the weights and all the biases, where we recall that the dimension of the parameters is quadratic in the number of units. Okay. Let me wrap this with maybe a few slides. First of all, this is an... so what I'm going to... I'd like to tell you why this perception model is so popular in deep learning, why people almost always use this perception form for the basis functions. There are two reasons for that. One is that it's computationally friendly, because it's mainly matrix products that you do. And modern hardware, modern CPUs, and especially modern GPUs are extremely powerful at calculating matrix products. They're optimized for that. The second reason is a mathematical reason. It boils down to the universal representation theorem. So we all know that, for instance, a polynomial regression offers mathematical guarantees, because combinations of monomials can approximate all smooth functions to arbitrary accuracy, as long as you increase the degree p of the monomials high enough. Hence, we know that polynomial regression, given a large number a large enough number of monomials can capture any smooth relationship in the data. Well, similarly, we have the same result for this perception neural networks, and this is called the universal representation theorem. These feed-forward ANNs that are represented here, they can actually represent any smooth function given enough units in the hidden layer. As you increase the number of units that you allow in the hidden layer, you are mathematically guaranteed that your neural network will be able to represent any possible function of the inputs, right? At least with provided some technical assumptions on activation functions, and we're back to your question, which all the activation functions that we have covered pass. So whatever your choice of the activation function, you are mathematically guaranteed that your neural network can represent any function. And that's why they're not of limited utility, you see, even though the activation function is your choice. If you increase the number of hidden units here, you can represent any function. Y can be any function of your axis to arbitrary accuracy. This is the universal representation theorem. I'm giving like a sketch of proof that will be, that's actually where I compare it to the well-known Carr-Madan formula, so it will speak to finance people on this link on Quora. So in conclusion, ANNs are superior to basis function regression because they learn the basis functions from the data. They don't force you to tell in advance what these basis functions will be. But they're still linear regressions that happen in the last layer. They scale better to high dimension because we can now regress on a limited number of basis functions. The neural network will find the training process is meant to find the most relevant, the best possible basis functions from the data. MLPs offer the same guarantees as basis function regression. That's the universal representation theorem. You know that given enough units in the hidden layer, you can represent any function. And they're also computationally friendly, as I mentioned. But what we don't have, is an analytical solution for training. This is the bit that disappears. We no longer have it. So we have no other choice than iterative minimization procedures, and these ones require gradients, all differentials of a cost function on every iteration, and the quick computation is derivatives is key to training in reasonable time. That's what we're going to see tomorrow. For this book, it's that I would like to recommend. I find it truly excellent, written by Christopher Bishop, who I think works, leads AI in Microsoft. And this is a technical book that very nicely covers the maths behind machine learning. However, it's been written before the deep learning era, so it does not really cover deep learning. But it covers very nicely and in very appealing terms for mathematicians and quants, the principles of machine learning and deep learning we are going to see tomorrow. Thank you very much for your attention.